In this practice video, we're just going to be doing a multiple choice quiz here, and I've put in my list of topics here, and we're just going to go through this, but I'm not going to look at the answers right off the bat. I just want to read the question, and then we'll try to get the answer um, from just reading the question. So, a rocket of instantaneous mass m ejects fuel backwards at constant speed u. Electric and gravity. What equation correctly governs the rocket's velocity? Um, we might have to like write down something here in order to think about it, but no, it'd have to be just guessing. Hmm. So we're neglecting the drag. Then I guess we have dv over dt probably has to do with some proportionality to the mass. Let's see. Which one of these could it possibly be? I'm thinking it's this. The change of momentum. Is that? Yeah, I'm not too sure. So yeah, I guess I'm gonna have to guess B here. We'll go to the next one. Okay, so a charged particle enters a region with uniform B and zero electric field with initial velocity x using charged particles. Which statement is correct? We'll have to read the statements to see what's not correct. Motion is helical with constant pitch proportional to Vz over B. I do think this is true. Motion is planar circular. Must be z equals 0. E- e- uh, I would assume it is planar circular because Vz equals 0. The speed increases due to magnetic work. Hmm. Oh, I see. Vy is 0, so it's planar. So yeah, this B is true. So C seems to be the most suspicious one so far. Trajectory is parabolic in the xy plane. XY plane. Speed increases due to magnetic work. Oh my god. Dude, I don't even know this. This question's crazy. Parabolic in the XY plane. Why would it be parabolic in the XY plane? I don't know. I'll just guess D. Okay, so a particle moves in the 3D under a central force plus a small non-central perturbation torque. Particle moves in 3D under a central force plus a small non-central perturbation torque. Okay, but non-central torques. Central forces don't apply any torque. So the external torque is causing a torque on the system. So angular momentum probably is not conserved because we have this torque from non-central perturbation. Angular momentum magnitude is conserved, but direction is not. I don't know. Both angular momentum and direction change according to DL. I think this is true. I think C is the correct answer here. Okay. The particle experiences a force derived from a generalized potential URV. Generalized potential, which is correct. So energy is conserved for any URV. A usual T plus V energy is zero only as U has a no explicit time dependence and no velocity. Energy is conserved as long as that equals zero. Energy conservation solely depends on whether the Lagrangian has cyclic coordinates. Oh my god. Which is correct. So I guess three of these are wrong. Only one of them is right. So usually this is true, but it seems to be pretty suspicious. So I don't think this is going to work because it doesn't matter if that's equal to zero. There's still a way to not conserve energy, I think. Whether the Lagrangian has cyclic coordinates. I'm going to think B is the correct answer here. Only if U has no explicit time dependence and no velocity dependence. That's what I'm going to guess there. Another one of these, which conclusion is valid? It's a 1D equilibrium point of potential V satisfies V naught x equals 0, equals 0, and V to the fourth is greater than 0. These questions are insane. Um, which conclusion is valid? V to the fourth. I don't even know what V to the fourth even means. I guess this is the fourth derivative is greater than 0. Well, how is that gonna mean anything? Stability, is associated with solving explicitly. This equilibrium is unstable, neutrally stable with simple harmonic motion. I mean, I'm gonna assume it's B, but like, I have to put a question mark because I have no idea what the question's even asking there. Like, how does this influence the problem? Anyway, so calculus of variations, a curve extremizes L. Which condition yields the Beltrami identity? Well, the Beltrami identity works if dx, if L doesn't have any x's in it. So L is independent of x explicitly is the correct answer for that one. Next one, holonomic constraints depending only on coordinates reduce degrees of freedom. Okay, yeah, that's true. Um, Lagrange multipliers introduce spurious forces that do no virtual work. Uh, yes, that is true. I don't know about spurious, but I do know that the things don't do any work. Um, Constraint forces don't do work. Spurious forces, I don't know. Multipliers enforce constraints but add non-physical kinetic energy. Multipliers enforce constraints but add non-physical kinetic energy. No, it's not true. Constraints can always be eliminated algebraically without multipliers. Constraints can be algebraically. I think you need the multiplier. Multipliers guarantee constraints satisfy Hamiltonian's principle automatically regardless of forces. Oh my god, dude. You know what? I'm gonna guess A on that one because the forces don't do work. I don't know. Okay, for an attractive inverse square force, what determines whether the orbit is bound or unbound? I think the second derivative has to be greater than zero. What? What determines whether the orbit is bound or unbound? The sign of the total energy. Initial rate of velocity. I think it's the sign of the total energy. I don't know. Okay, we're almost done. We got 10 questions. So for two equal masses coupled by three identical springs between fixed walls, mode frequencies are W1, W2. Okay. Both modes correspond to equal phase motion. One mode is right, the opposite. I think the answer is B here. One should have equal phase, the other one opposite phase. I'm just taking a guess, I think, but we'll have to see. Electromagnetism, so it says in a source-free region outside a local charge, what statement is correct? Only the monopole term can exist. Source-free region outside a localized charge distribution. Man, I don't know. I think I have no. I don't know. I don't know about that one. So yeah, we're just gonna have to see. There's a bonus question. Yo, what is going on here? Okay, whatever, dude. So let's look at the answers here for our 10 questions. I did really poorly, didn't I? I mean, 6 out of 10. I'd be nice with that kind of score, I guess. On some kind of exam. Okay, so what is this? Rocket equation? Um, yeah, that's how hard these questions are. It's so hard, man. So, rocket equations is correct A. It's mv equals negative um mass. And I guess that's, yeah, see, it's sort of the derivative of the potential, sorry, the derivative of the momentum here is equal to some proportionality constant times the drain of the mass. So what I was thinking was actually correct. Anyway, we'll have to do these questions one more time. We're going to repeat the quiz and see if we get a better score after we look at these answers. So charged particle in B, velocity decomposes into circular motion in Vx, uniform motion. What is happening here? Helix. Magnetic fields do not produce parabolic trajectories. Correct is A. Net motion is helix. What was the question here? Well, I think I answered that B, right? Why did I put D? What the hell? I don't know. The answer here was A. That makes a lot of sense. Okay, let's go to the next one. Angular momentum with torque. Any torque changes angular momentum, magnitude, and direction. Yeah, this was correct. This one here, energy conservation requires that. Velocity dependence breaks standard conservation. Stability test. With this, potential minimum is quartic instead of quadratic. Motion still stable, but not simple harmonic. Hmm. I guess that would kind of make sense. You got the fourth derivative is positive. So you have a stable condition. But it's not simple harmonic because if it doesn't have the second derivative uh, greater than zero. Okay, okay. Beltrami identity. This was correct. The Lagrange multipliers do no virtual work. I knew it. And B, central forces, is just, yeah, the energy is what determines them. Normal modes was in phase, out of phase, and the multiple expansion, all multiple terms are allowed. All right, well, that seems like a pretty easy quiz. Let's try this repeat questions again. And so now we should be able to get these quite perfectly. Remember that this is going to be like this is the time derivative of the momentum here, and then there's some proportionality constant with the drain of the mass. So that's A. This one here was all about the helical motion. And this one was about changing momentum due to the torque. This one here, energy velocity. Yeah, this is about time dependence for the potential energy. So it is about stability versus the fourth derivative. So see here. This one was the calculus of variations. The Beltrami identity is for A, is independent of the base x. The Lagrange equation here introduce constraints that do no virtual work as A. For the motion under the attractive square force law, so the sign of the total energy only. Coupled oscillators. This was one mode in phase and one mode opposite phase. Over here it says apparently all multiple terms are allowed. And there we go. This should be 100%. Yay! Alright, so that was the quiz drill. Just looking at some questions based off of the topics that we're working on, trying to make them like super hard, and then figuring out what the answers are. Let's drill. Rotational motion. Um, Actually, that does sound like a good idea. Let me do a question on rotational motion as well. Sorry for the wait there, but unfortunately, I don't really have a chat window to look at. Can we do, let me do like two questions on rotational motion as well, just for fun. So it says, a rigid body rotates with angular velocity w that's not aligned with the principal axis of the inertia tensor. Holy smokes. No external torques act. Okay. Uh, if no external torques act, then what the heck is this? Both W and L remain fixed in space? In space. The body exerts free precession because W changes direction while L remains fixed in space. Not aligned with the principal axis of its inertia tensor. No external. Holy smokes, this is kind of hard. The angular momentum vector remains fixed in the body frame. Angular momentum velocity vector remains constant. But I think the angular velocity vector remains constant in magnitude. I don't know about the direction. So I'm gonna guess it's C here. W should change the direction while L remains constant. I think it's C here because there's no external torque, so things don't change too much. Here's the next question: is a uniform solid cylinder rolls without slipping on an incline of an angle? This is a pretty classic question. The statement is correct. I'm pretty sure this is the correct answer right here, because I do recognize this equation a bit. But let's see, static friction does negative work, reduces mechanical energy. Not static friction, no. It does no work. It's static. Translational acceleration is g sine theta. Translational acceleration would be like this. I mean, it could be, but I think it has more to do with this because IA equals RF. Is kind of an important, I alpha equals RF is a really important thing when you're doing rolling problems. So I still think it's C here. Rotational energy exceeds kinetic. Submit answers as that. Oh, let's see if these are the correct answers. Aha, they were correct. Pretty cool. Yeah, just kind of the intuition here for this one was that again, the idea that since no external torques act, the angular momentum should be constant, but of course W is changing directions, and it's called W for a reason there. So yeah, and then this one was again that I alpha is equal to RF, and this force here is acting on the cylinder, but it's not the acceleration, it's the force, it's the torque, really. RF. I mean, we didn't put an R over here, but um, that kind of cancels out. This should be like I alpha equals RF. I'm pretty sure, but you know, obviously there's different ways to solve these questions. Anyway, hopefully this was kind of helpful, and